Um, I have started live stream. Good. Good news. Good sharing. You got the tutorial sheet to share. You can just go to those, start solving problems. So all the problems are completely optional. But if you feel that you're unfamiliar with the basics, just go through them and see which one you can just to get a good form of subject. But otherwise, you can directly go to the main problems. Some of them are from topics not covered, but I discuss them as required, then when required. Tell me which solving. Welcome back, everyone. I already shared the tutorial sheets on the WhatsApp group as well as Teams chat. You can just have a quick look at the long exercises and probably you don't need them. So you can, if you're comfortable or confident with those, then go ahead to the main problems. And you are supposed to solve this, and I'll just be there to help or guide you if you're not able. Online participants, please raise your hand or post your questions in the chat. Thank you. Yes, if anyone has already solved the problem or you already know how to solve the problem. Maybe I can do some of this while you look at the video. One is we have the commutative diagram based definition of roots. How can you also define a region group using the same method or same in a similar manner, same approach? Actually, you of course need to define some new map. It's not possible. So the new map is given the hint, but you can also think about it. You want to define commutativity, right? Commutativity means when you change the order, multiplication gives the same result. If you understood how commutative diagrams work, you just need to think about this. When you change order or don't change order, multiplication gives same result. Commutative diagram means what can you do? By the way, if you are solving harder problems, you already know this, don't pay attention to what I'm saying, just continue solving it. You want to listen on that. So, commutative diagram, the only thing that you have available to you is composition of functions. You can only equate composition of functions by saying that a diagram commutes. Using composition of functions, you need to express the idea that when you change the order of arguments in the operands in the operation, the result remains the same. Okay. So obviously changing the order is not possible unless you define that after applying the operation changing the order, that is not possible to do it using any function. Before applying the function itself, you need to change the order. That means you need to define a function. Obviously, you need two arguments from G cross G. After changing the order, you still have two arguments. So 2G cross G. Let's say this is tau. Constitution of twist. Okay. It's just maps x y to yx. Okay. Visible but this. So now this is all you need. Using this, you can definitely think about how to express commutativity as a that is commutativity of a given binary operation using commutative diagram. Again, the idea is the only thing you can do is equate different compositions of different functions. So what I want is what I want to say x dot y is equal to y dot x. Also express this as composition of functions. Clearly, x dot y means what in terms of the function? If you have a multiplication map, then x dot y is just m of x, and y dot x is m of y. Then you're done because inside there you just have to use that one. So this is just m of x, right? Which is that. So here you have m of tau of x. So this you need to write as a diagram. That's very easy. So you have this form. You can easily express it as a diagram because domains and codomains are evident from the functions, right? Ultimately, you get something in G. After applying it, you get something in G. But the arguments are from G cross G, x, y, and y, x. In fact, both are x, y. So that is from G cross G. So this x comma y is from G cross G. And ultimately, the two things you need to get there are x dot y and y dot x. These need to be equal. So two ways of going through this diagram to give you these two different things. But then since you say the diagram commutes, they must be equal. So what is here? This row say M. The other M after tau. Starting point is same. That's the point. Observe that the starting point in both cases will be xy. So that's when you know that you got it, because the starting point should be same. The ending is of course the same because they're equal. So when the starting gives the same element from one set. Right. So this is M after tau. So what should that set be? Tau is 3 cross 3. So if you say this diagram commutes, that's equivalent to saying this. In fact, that's equivalent to saying this. Xy equal to y. So apart the four diagrams that we saw in the morning, we say this also commutes. That means the group is immediate. Okay, where is the multiplication group operation? Or then you have to define this map out. Very often you are able to express some of these things, whatever axioms you have in terms of elements, by defining certain maps. You are able to express them in terms of functions and commutative type. Again, the advantage is this: you can generalize this to different settings. Now, this is in group, but you can generalize. So, when we study categories, we see exactly how. But to give a simple quick example, this we did with just sets. But now, suppose we say that instead of sets in Z functions, these are topological spaces and continuous functions. So, I'm replacing whatever sets we have. These now not just a set, but a topological space. And these whatever functions you write here, they are not just functions, but continuous functions. Then what do you get? What is this D that you defined? You are defining them still a group, but it's a group defined in a topological space such that the group operation is a continuous group. Okay, and the inverse operation is already that's also continuous. Whatever functions right, they must be continuous. So group operation is continuous mark, inverse operation is continuous mark. Okay, and the map that gives you the identity that is continuous mark. So that will define what is called a topological group, which some of you might know. Similarly, if you have any particular kind of structure, and then you apply this definition to that structure, meaning whatever structure you have, whatever mathematical structure you have, and then you have homomorphisms of that structure already defined. Then if you replace the sets here by that particular structure, the underlying sets of that structure, and then the functions you replace by no, meaning you insist that these are not just functions of the underlying set, but they are homomorphisms of that particular structure. Then you will get what is called a group object in that category. That means you will get a thing that is simultaneously a group and also whatever mathematical structure you have, graph if possible or anything. Okay, which is simultaneously a group, not just a group in some arbitrary way. It is a group in a way that is compatible with the existing structure. So, of course, I can take a set and define some group on it. I can define cyclic group if it's finite or incomplete. Or some other group I can define on. That's not the point. You can define it if it satisfies these commutative diagrams, then it will be defined in such a way that it is compatible with whatever mathematical structure you have, be it a topological space or anything like that. Okay. Now there is an interesting question. What if you say that these functions should be group homomorphic? Are these functions group homomorphic? We are defining group using the set and functions. So that's the definition of group. But suppose I say that before starting only this should already be group and these should be group homomorphisms. Then what happens? So maybe we'll see that later. Think about it. It's not that simple. It's not that it is already. Okay, for example, here example the inverse mapping. We have this inverse mapping. So D2G, which ultimately does what? Maps every element to its inverse. Will that be able to move on? That's one of the form of exercises, I think. Yeah. Problem 5 in form of exercise. Part 2. To define function I from G to D, I of x equal to x inverse. That will be a homomorphism from G to itself. Homomorphism of G is homomorphism of G to itself. If and only if G is a real. Okay. Actually, this is a simple exercise well known to you. It is usually not expressed in terms of homomorphisms. I will just rephrase it in terms of morphisms. But it is usual problem is what? If it is true that in a group xy inverse equals x inverse y inverse for all xy, then the group is a real. If and only if it is a real. Okay. In terms of homomorphism, you can say that this map should be homomorphism or endomorphism. Why is it the same thing? Because endomorphism or homomorphism condition is f of xy is equal to f of x, f of y. Correct. So if f is the map that maps or I is the map that maps every element to its inverse, then in that particular case, this becomes xy inverse equal to here you have x inverse, here you have y inverse. Whereas normally xy inverse is always equal to y inverse x inverse. That's universally true in any group. But if you say that the group satisfies this property, that means it must be linear. Or even if you say that the two elements x and y satisfy this property, then those particular elements x and y will come in. Locally, it means two elements x and y satisfy this property, they commute with each other. So if all elements satisfy this property, the group is complete. Okay. So these are not the functions involved in the definition are not themselves group homomorphic. Okay, they are just functions. But if you now apply that what I said and take the collection of all groups or specifically the category of all groups, and then say that all these functions should be not only just functions but group homomorphic, then you will get actually an MBA. But that's not obvious. It's not this simple because I can say that this may not be the given group's multiplication. This may be some other map on the group and so on. So there is some proof required. So we come to that later maybe. Okay, let's see. Anyway, we'll move on to other problems. Anyway, we'll deal with that in time. Second problem is well known to you, law of exponents. Usual familiar laws are valid even when you're taking powers of groups. I mean, powers of group elements. Suppose usually corresponding to exponents, you also have roots. That is one thing. The roots may not exist in the group. I mean, even in real numbers, roots don't always exist. Correct. Square root of -1 does not exist in R or to extend the field, right? So similarly in the group, there may be n powers will always be there, but n roots may not always be there. And another thing related to exponent, other than roots, one more kind of inverse type of thing, what is it? Related to taking powers. One sort of inverse, one thing that's like inverse is taking root. Another thing like inverse is inverse exponentiation. Logarithm. So again, you can ask log in a group also. So that is the discrete log problem. Specifically, you can ask in cyclic groups, but also in general groups. That is a discrete log problem, which is again difficult. Okay. In fact, I think those who work in cryptography will be knowing. Discrete log is difficult one, and that is the basis of some of the algorithms. Right. Because it is difficult, we have some algorithms are second. Okay. Yeah, another simple problem here is, which I just want to mention, and saw that PFD is a monoid. So it has an identity element which is singleton set E, where is identity element of the group. Does the monoid have units? Unit of a monoid is an inverted plane. So monoid is not by axiom, by axiomatically monoid does not have all inverses, but some elements may have inverses. Some elements x may have to element y, such that x y is equal to y is equal to e. Which are those elements, if any, in monoid? Of course, identity elements are always separate. So at least one. Are there more? If you take any other element, then is it possible that is it possible? Yes. Singleton, right. So if you take singleton set, suppose that will be some group element, so set of offsets. So is this possible? Yes. If X is the inverse of the element G inside the group. So then that is possible. Is that the only possibility? For that you would look at the previous question also. Cardinality of AB is somewhat unique. Is at least equal to mean. AB or more simply the set AB is at least as large as both A and B. Okay. In the if you take unless one of them is empty. One of them is empty, then of course it's zero. But this is at least as large as both A and B. It means it is max greater than or equal to max of So if you don't take a singleton set, then what happens? You cannot make singleton set as result. So these are the only units. Okay, so the units of this are exactly singleton sets with the group elements. Means so subgroup subgroup of group is there, but you can also define subgroup of a semi-group. It is a sub-semi-group which happens to form a group. Similarly, you can define subgroup of a monoid. It's a sub-monoid which forms a group. Okay. Or in fact, sub-semi-group which forms a group. Maybe the identity element is different, that is possible. But here, yeah, this sets of this form, singleton sets of this form, will form a subgroup of this, which is isomorphic to the group G itself. Okay, we did not discuss isomorphism in great detail, but you already know that. Yeah, and some of the familiar properties of homomorphisms such are already defined. Another thing is what is the idempotent of this? You have first of all an idempotent usually denoted E, but here we are using E for idempotent. So I'll just write X. So an idempotent of a semi-group is an element X whose square is itself. It not to be confused with involution. What is involution? Square is I means E, identity element. Okay. There is some other notion of involution also. Okay. Yeah. So square, it is square, it is self-inverse. Self-inverse and it is involution. This is not involution. Usually we get confused. At least when you remember the first time you get confused. So x square is equal to x square. What is an idempotent? When will a square be equal to a? Or actually not, it's not a nice answer in that way. You just describe what it means for a square to be equal to a. Yes? But A is an element. A is an element of P star of G. Yes. Just remove it's a semi-group. In what sense? As a subset of G. That's correct. A square is equal to A. That's correct. As a subset of G, it must be a semi-group. So what might possibly be missing in that form that prevents it from being a group? Maybe inverses are not correct, or maybe identity element is not. Even that is possible. Can you give an example of a group with subset like this, which is not a subgroup? So the simple case is when A is a subgroup. So if X is a subgroup, so it's a sufficient condition but not necessary. Then we already saw X square is equal to X. But even if it is not a subgroup, as you see, if it's a semi-group, then it is possible. Any example? Then you take significant set with order to element, you will also get E when you multiply it with this. Okay. So under addition, so you take so remember that adding power becomes multiplication. Multiply, not power. So if you have addition notation, so we swap powers in multiple. Okay, so under then you take significantly or non. Okay, what? Strictly positive. I'll use this. Okay. Then what happens? What is the operation addition? So when you add elements of this to itself, what do you get? Definitely a subset of this. So positive variable, when you add, you will get positive variable. Is it equal to this? I want it equal. Is it equal? Because 0 is not. But these are real. Okay. If you took natural numbers, then it won't be. Okay, for example, because minimum you have to get to. But since you're taking real numbers, you can take as small as you want. And actually, it goes to analysis also. Usual trick. When you ultimately want to get some fixed epsilon, what do? Sometimes you take start with some epsilon by 2. Okay. All the epsilon is arbitrary, epsilon by 2 is also arbitrary, but you say take epsilon by 2 in the beginning. Similarly, here if you want to get a particular real number, as a sum of two real numbers, just take half of itself and add it. Yeah, that is correct. So it's very good. So in particular, it is such and yes. So this is also an example where I already mentioned that as a theorem, not prove it, but we prove it now. That if H is finite, then this also implies that H is a group. So here, this is not implying that H is a group. H is a subgroup. Okay, this at most implies that it's a semi-group. That's right. But if H is finite, so together with this, this implies that H is a subgroup of G. Same thing already. H is a subgroup of G. How? So this is an example where you definitely need finite. This is also satisfying this, but it's not a subgroup. So without finiteness, you can't have the integration. So why is it proven it's finite? So x squared is equal to try to consider so if x is a subset of G, which is finite, then x square equal to h implies h is a subgroup of G. Again, reminder, x square doesn't mean square of elements of h, means all products, all binary products of elements. If you take two elements from it and multiply them, all of this together, that is x square. Okay. Okay, yes. That is from what property to cancellation. Cancellation tells you that which are distinct arbitrary x1 into x. X1 into x. So you are going to take x1 into all the elements. So these are all distinct elements. That is true.
That should be first x and h1.
So you know already that because it's closed, it is a subset of H. Okay. But because they are all distinct, how many of them are there? N. But if you take a subset of size n of H, okay, where H itself is of size n, then that subset must be H. Okay. So this is true. And this one, if I call it, yeah, in fact, I call it x1h. Okay. This is x1h. We already have the position. This is equal to this because of cancellation. So that implies x1h is equal to x. Yeah, okay. So you got it. That this is equal to x. Fine. Then
X1 and xj equals to xj.
there must be. Wait. That doesn't count. X1 into xj must be equal to xj, no. X. Yes. You can't say that for some j. Which j is that? It is not j actually. X1 into something must be equal to x1. X is there in h. But we just said h is equal to x1h. Therefore, what? Not really. X is there in h, but x is x1h. So that means x is there in this, not x. Sorry, x1. Yeah. So, oh yeah, and I have to. Use the pointer when I'm pointing actually because otherwise I only got some. Okay. So yeah. Anyway, x1. Oh. Okay. So x1 must belong to x1h, which means x1 is equal to x1 times something. That will be. Now what? Yeah, so by cancellation in loops, xj is equal to the identity element of the loop. Okay. So you can, for example, write x1 as x1 dot e in G. Okay, let's write x1. We are not assuming that e is in it. It's simply saying in G x1 is equal to x1, but that is also equal to x1 j because it's happened to e as well, so it's equal to e. Okay. Clear. Cancellation is valid. So you can do that. Then what? E belongs to H. Okay, I mean E belongs to H. Yes, agreed. Then, yes. Yeah. So next, since E belongs to H, which is equal to x1 H again. So x1 into some say xk must be equal to E. Now with xk is x1 inverse. So x1 inverse also is there, and this obviously the argument works with any xi. So for every element, its inverse is also there. It's already closed under the operation by exception. The inverses are there, identity element is there, therefore it's a subset. There is a similar problem which I think has been given in the tutorial. Any finite cancellative semigroup is a group. Very simple. Finite cancellative semigroup is a group. Cancellative means the laws of cancellation hold. We are not assuming the existence of inverse, only the cancellation. Is it true for infinite case or okay? Obviously not, because I've stated this way. Quick example for why it is not true in the infinite. Cancel it. So the earlier example actually works for that. Okay. Oh yeah, I said if and only. Yes. Oh right. Yeah, because of the definition I have stated at that point. But actually, like in the basic group properties, once you establish those, you actually see that one multiplication is enough. If x into y is equal to b, then y into x has to be equal to b. Okay, there is no other way. In a group, assuming that it's a group. So, for example, in matrices, it's not. You take two arbitrary matrices A and B, and AB is equal to identity matrix. BA may not be equal to identity. BA may not be defined first of all. If AB is equal to I, then no, if AB is equal to I, then BA of course will be defined. BA will be defined, but of a different order possibly because I'm taking rectangular matrix. But even there, if you take two square matrices A and B, and if AB is equal to I, then BA will be equal to I. Okay. Only for rectangular matrices it fails. So that's a special case actually of the thing where if you have two functions like between two sets. It is possible that, for example, F composition G is equal to identity element of B, but G composition F may not be equal to identity mapping of A. That is possible. So we can see similar case first when you take R into Rn. This is some you can consider an m by n matrix. This is a mapping from this one, and then this will be n by n. So unless n equal to n, both the compositions cannot be n. Like simply in algebra to do that. So yeah, that's what in groups is not. Even for square groups it's not. No, you already know it's a subset of the G is assumed to be. That's it. We are not doing construct as a group. So already subset of a group. Okay, goes under operation. And it's finite. So from finite means closure and under operation, the code is a subset. Okay, starting from the group. Here it is. It is not. Here you have to prove that is a group. But there is another exercise again which I have not included, but it's an interesting exercise. That if you just assume in the group assumes, we usually write for simplicity that E x equal to x, E is equal to x, x y is equal to y, x equal to E for some y corresponding to x. But that's not necessary. If I just write there is an element E, such that for all x, Ex is equal to x, and for any x, there is an element y such that I think they have to be paired correctly. Okay. Yeah, left identity, left inverse. So if you just assume that left identity exists in the set, in the semi group, that's it, and left inverse exists for every element, this will still define it. You can still prove with this much that it's going to be true. That means you can prove that together, if you use this and associate with it, then you can prove that x has to be x as well, x y has to be e as well. Okay. So in fact, we don't need all those assumptions in that. Okay, so find cancellative semi-group. Basically the same argument, right? Only that you don't have identity already, so you cannot cancel to get that. So what do you do? In a group, as soon as you get x into y is equal to e, or x into y is equal to x, you can say y must be the identity because it's already there in the group. Here you are starting with the semi-group. You don't already have a group with an identity. So you have to show that there exists an identity. Cancellation cannot be done. So cancellation semi-group, but cancellation cannot be done because you don't already know such an element. Okay. See, what does cancellation mean? What does law of cancellation mean? If you have already got, for example, ax equal to ay, then you can cancel it and say x equal to y. Suppose I know that in such a group, for one particular element x, I have ax equal to x. Can I cancel this and say a is equal to b? No, because this is not in this form, right? I need to know that there exists some element like that. Now I have ax equal to x and by is equal to y also. Again, can I cancel this somehow and say a is equal to b? No. Right? That is the thing. So you can't assume that there exists one element acts as identity for all the elements, and then cancel it and say that this must be true. So somehow you prove that it works. But again, argument is basically the same. Yeah, you can start. So let's call it G only. G is the finite cancellation. So you put using element of G. Then it is true that you multiply, you borrow that notation and say that this is the subset of G obtained by multiplying X on the left of the element of G. Then we know this is the subset of G. But because G is cancellable, you can actually use the same argument of counting and say that this must be in fact equal to. Okay. So because of cancellation, that's all you need for sorry. Okay. Cancellation is all you need for saying that this must be equal to the coordinate, right? So yeah, therefore you have xg is equal to g, okay, or gx or whatever. So this implies that there exists some let's call it e. There exists e such that x e is equal to x. For that particular x, if I restart the argument by taking another, I know that x is arbitrary, but if I argue this again by taking an element y, can I then say that y is equal to x over y? So it may be some other. I have not done nothing to do with this e is unique element with this property. So that is not somehow to do with this e works for anything else also. Possible. Same thing with the identity element. We know that actually, if it is actually true, if the statement is actually true, then this must be the identity element of the group. So we can use the fact that we secretly know this. So knowing that what should you do? That is the thing. So guess what to do based on your core knowledge that E must be right. Right. Yeah. So that y is also equal to y for any element y. For any element y. Now we don't redo the argument. Now this E is fixed. Now show that y is also equal. So we can find that same quantity. Okay, y is equal to y or so x is equal to x now. So yx is equal to yx. That is um, so on. Problem is E is on the wrong. Yeah, translation. You can't cancel x from the middle. That is the problem. In the left or cancellation in both left or right cancellation is there. You can cancel it if it's on the left or right. But in the middle there is no cancellation. Let's see what it you're taking arbitrary y is equal. Okay. 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 Then okay. So you want there. Means y dash equal x. Okay. Ah, okay. Yeah, that is a better way. Okay. You have to show that Ex is also equal to x. Okay. How to do that? You know that there is some element E prime because this argument does not really use anything special to left or right. So the same argument works if you take gx. Correct. If you take gx also it works with the same x. Same x equal. With same x equal to then what happens? Similarly, there exists some E prime so that E prime x is equal to x. Okay. That, okay, then what? Wait. Are you showing the E prime is equal to? No. Okay. Fine. Okay. I will continue with that and then we will come. Yes. X equal. Right. Okay. Oh, okay. Yeah. Oh, all right. Okay. All right. Yeah. Good. So then, so if E prime satisfies this, then you get y is equal to E prime y. And y is arbitrary. So from y is arbitrary, you also get it is equal to. Yeah, because you already know. Yeah. This is for arbitrary y. Alright. This is even follow the arbitrary. Y is equal to x y prime for some. Yeah, because correct. So that's how you are indirectly using that. Yes. Um, okay, this is also true. Then what? E is equal to prime, right? Yes. E prime is equal to x. Yeah. Okay. No, here x is equal. No, that's what. We can't change for it. Right. That's why we need to keep prime first of all. Otherwise, we know E itself works. The problem is we can't even assume that it's the same. Okay, we can't even assume that E and E prime are same. You have to show that. That's all. Order thinking not possible because computation is not. How to get E prime is equal to. Okay, so let me try. E prime E is equal to E prime B square. Um, E prime. Can I not say two arguments? Actually, that's what. Whatever argument we used here, right? So what did we establish here? That e prime x equal to x. From there, whatever you did, without using e, right? Just using e prime and x, we showed that this is true for all y. So if you now start with this one, that is x equal to x. Similarly, what does it imply? To make the same argument for x is equal to x, then what will that give you? Y is equal to y. Give you y is equal to y for arbitrary elements y. That's it then. Because this is true for y equal to e prime, and that is true for y is equal to e. So from there, you get that. So here you can take y is equal to e prime. So that gives you e prime times e is equal to, and the other one is here you can take y is equal to e. That gives you this side. These must be equal. Here in the special case, we take y is equal to e. You get e prime is equal to e. But here is a special case if you take x is equal to, sorry, y is equal to e prime, you get e prime, the same e prime is equal to e prime. Therefore e is equal to e prime. Okay. Yeah, then the inverse argument is same as nothing new. So identity element already exists. The inverse argument is same as. Okay. That is just xg is equal to g, so x into something must be equal to e, that must be the inverse of x. Like I said, it's enough to prove one-sided inverse. Once you have identity, it's a monad, you have every element has one-sided inverse, then same side, on the same side. Then it will be true. Okay. Any questions about this? Okay, these are still long questions. Go ahead. Homomorphisms. Basic properties of homomorphism 0. Any homomorphism preserves identity. This maps identity of the domain group to the identity of the codomain group. It preserves inverses. F of x inverse equal f of x inverse equal to f of x whole inverse. Actually, more generally is given there. F of x to the power n, where n is any integer. F is a homomorphism. F of x power n is equal to x power n for any integer n, including minus 2, so that's inverse. So that's how we define it. Okay. Those are the basic properties you already know this, and composition of homomorphisms is also homomorphism. Fine. Okay, let's take up the slightly more interesting problem. Again, these may be different, but let's see. Just for sake of recognition, F is a homomorphism from G to H. What is meant by image of F? Usual as a function image, right? So you can either write y belonging to x such that y is equal to f of x or something. Right? So use simpler notation, although the other one is strictly more correct. But I'll more simply write this. Okay. Considering the subsequent points. Okay. The other one is slightly more correct notation, but this is also fine. Well understood. There is no argument. And what is kernel? Kernel of F? Set of all elements of G such that f of x is equal to 1, means E image. Again, we can just write E because it's understood, but it will be clear, right? Of x equal to the identity. So this is a subset of what? G. Okay, and you already know these are in fact not merely subsets but subgroups. This is also well known. Fine, just keep it in mind. No other subgroup and all will be complete. So the first tutorial problem, the actual tutorial problem, first one, part A. B is the group of groups. Part A. Uh, part A is G is an element in G. So fix that. Fix an element G. Define mapping FG, that's of G on G3 by FG of X equal to X G inverse. Is it a homomorphism? In fact, an automorphism. It's a mapping from G2. And then mapping in the function. Is it an endomorphism? Is it a homomorphism? Again, this is somewhat well known to do this. Okay? Maybe we will do it. It's the more interesting second part. So, so what is the operation called if you fix G and do G plus for all X or for given X? Conjugation. This is called conjugation. Okay. This is conjugation of X by G. The operation is called conjugation. Not to be nothing to do with complex conjugation. In matrix theory, we would call it similarity transformation. You do PXP also, which you are familiar with in diagonalization, for example. Okay, why is it a homomorphism? So we take G of xy. So remember, G is fixed. We are not changing G. Understand the mapping clearly. G is fixed. We are not changing. The mapping takes different elements x. X is arbitrary. Okay. So you take two different elements in place of x. So for it to be homomorphism, you know f of xy should be equal to f of xy. Here f g of xy should be equal to f g of xy. So f g of xy by definition is g xy g inverse. Okay. So this requires some foresight, but if you start from the other direction, it's actually simpler. Ah, yeah, but if you can't see that, you can't see that you have to insert G inverse G in between. Just start from the other. So if you are so in general in a problem, right? If you are trying to do adjacent to the RHS, you start what you do? Try RHS. Maybe both will reduce to C, or maybe RHS will reduce to adjacent both C. So if you start with the other one, it's easier, but here and here will go with this. So just realize that you need to insert this in between, and why is it valid to insert some arbitrary element in between? And see, G inverse is identical, so you can always multiply that with anything without changing. And so this is FG and this is FG of x and this is FG of y. Yeah. But obviously, if you started with the RHS, you would have this, and it's easy to see that you just have to cancel. So that's why it's easier to start from here. Okay, so this is clearly a homomorphism, but it has to prove that it's an automorphism, which means you need to addition to that is hygiene. Yeah. Either you have to prove that it's injective and surjective as function. What is the other way? Prove that inverse, existence of inverse explicit. Okay. So what do you think will be the inverse? This is defined for any system. So G inverse x, that means FG inverse. So consider FG inverse. This is defined like this. G inverse in place of G. So in case of G inverse, you will have G. Okay. Then consider the composition. So Fg after Fg inverse. Okay. Um, what is this composition equal to? So actually, I'm supposed to write this on x is equal, but I simply write this is going to take x and map it. So you can also write function in this notation, right? X maps to, so you can also write x maps to this notation. Right? Instead of writing f of x equal to something, you can write x maps to whatever. So here I'll write this x maps to what under this. So I'm applying Fg inverse first. So it maps to Fg of, actually it maps to Fg of Fg inverse of x. This is Fg of this thing, that is equal to G of G inverse of G inverse. Clearly, you can do cancellation here as well as here, here x. So that means this mapping is identity. That means this mapping, because it maps x to ultimately x. It is identity mapping of G. Is that enough? I mean, does it prove that this is inverse of this? It proves that it's right inverse of this. To do the other one, but actually you don't need to do the other one. One reason is okay. So one thing is you can think it's a mapping from G to itself, and if it has a one-sided inverse, maybe that's has to be good like square matrix case. But even without, I'm also not sure. So even without that, G is itself arbitrary. So if you took G inverse in place of G, here you have G. So that immediately gives you don't need to do this again. So by replacing G by G inverse, you immediately get the other one. Okay. So therefore, this is the inverse. So the composition is identically mapping both ways. That is an inverse. So we know that homomorphism with an inverse is an isomorphism by equivalent. Okay. So therefore, because it's an isomorphism with the inverse, it is an automorphism. The second part is the more interesting one. And next, wait, one level higher because what is this thing? What is odd? Set of all simply set of all automorphisms without saying what. This simply set of all automorphisms, a set of all alpha from B, which are isomorphisms. So automorphism obviously. Okay. So in the notes in the game, you can refer to the notes during this for definitions and any theorems which are required. Set of all automorphisms itself forms a group. Take a group and consider set of all automorphisms on that. That itself forms a group. That's why I said it's one level higher because we're not talking about group elements, we're talking about functions defined in the group. They together form a group. How is it? What is the operation here? Function composition. Okay, and it's a group because you already know any isomorphism has an inverse. So here and identity mapping on G is an automorphism. So the identity mapping on G is an automorphism, and if alpha is an automorphism, then so is alpha inverse. Alpha is an automorphism, it's identity, so inverse exists, and the inverse also must be an automorphism of G. Okay. And of course, function composition is associated. So it's a group. Now this question says, consider the mapping from G to odd G. So what we have now is for every G in G, corresponding to every G in G, we have an automorphism. We already proved that before. We have an automorphism. Define that as a function from G to or G, which is also good. Now it's asking you to do that this is a homomorphism. This phi is a homomorphism. What does it mean? Yeah, okay. Simply means that phi should be positive and then phi of GH if you take, this must be phi of G, phi of H. Okay, so the question is the first one. So I'll write this question. So replace phi with the actual definition. What is phi of GH? F sub GH, which is explicitly defined, right? This is a function that is explicitly defined, and on this side you have fg, and what is that? Okay. Yeah, I took G inverse or G inverse G inverse. Right. So I should have taken myself. I should have taken G inverse. So just modify the definition. So I'm going to modify the definition where x max to G inverse. If I understand correctly, this should work, not the other. Yeah, this is going to work, not the other one. Is it? You already checked. If you get here, you get check equals inverse. It is equal to x. Okay. Actually, yeah, yeah. So, no, it's like this. No, I don't think it was either. Okay, we'll take the other. So again, the question is this true? So on this side, x max to what? Again, you have to equality of function mean they act the same way of the set. That means every element maps to the same element at the both. Right. So here if you take x, x maps to what? dh x dh inverse, which means dh x h inverse inverse. Okay, that's not right. What would the other side? fg fh x. So first order fh. So fh maps x to what? Plus fh maps x to what? First order friend. X x. Oh yeah, it was right. X x. But then you have to apply fg. So in fact I like that. So so this is fh maps this, and then fg maps this to g bracket with g. Right? Okay. Right. So we are right. Yeah, I will remember that you will take the other operation in order to make this. Actually, that's what we do. Yeah. Oh yes, I got it. That is, so there is a notation for this. If you are G exhibit, there is a notation for this. It seems saying that x to the power g. G is not an integer. The integer power of group element is well defined. G is another group element. What does it mean to raise the power, raise in one rupee to power? That's not power at all. But why do we use this notation then? Because this also satisfies one of the laws of exponents. Means under this, you write power t whole power x, it will be x power t. Basically same thing. But for that, we have to define it this way. Because after the x power 3 yeah, that's exactly the thing. Here fh gets applied first. There x power g gets applied first and then h. So if you want to work it, if you want it to work in this order, then you have to do g equals x. Then it will work. If you do gx equals like this, it will not work out. You will get x power hg, which is unequal. So in fact, for this, there is sometimes very strange notation, left side exponential. Because then if you do x power g power h, it will be x power hg on this side. So then you apply g first, not h. So use this notation, but it's actually useful notation sometimes. Right. So, okay, since you already know about image equality, let's see. So, what is the kernel of x? What is kernel of x? E is it? Suppose G is an abelian group, then what is that G? Huh? G, if G, suppose the extreme case, G is a abelian group. In that case, what is that G? And G of x equal to x. So if G is ideal, what? What's it called? Not identity. Because identity mapping. Correct. I'm sorry. I'm thinking of the other mapping. Yeah, correct. G of x, yes, that is correct. I'm thinking of fine. G of x equal to x, that is identity. That's correct. So in that case, let's see. I want kernel of f. So kernel of f in that case is equal. In that is correct. But in general case, oh right, right. The conjugate here. I think I'm thinking of 5 and I'm thinking. Correct. That is correct. Kernel of f is equal to opposites. We already proved it's an orthonormal. Right. That's complete. What is kernel of what is kernel of 5? What is kernel of 5? Yes. Yeah, that is G is abelian all of G because first of all, kernel of phi means what? Those elements of G that are mapped to what? Identity of odd G means identity mapping, not identity element of G, because that doesn't make any sense. It's identity mapping. You want FG to be, that means phi of G is FG. You want FG to be identity mapping. When will FG be identity mapping? So one case is where G is abelian, then whatever G you take, FG will be identity. That's true. But otherwise, so if FG is identity mapping, that means FG of X equal to X for all X. That means Gx G inverse equal to X for all X. Right. Dx again, for getting right large enough. Okay. Right. So Fg is equal to ID means maps of simply Dx inverse equal to X for all X. That means G is, or another way to write this, Dx equal to Xg. So G is, yeah, G is in the center of G simply defined as the set of all elements that commute to all the elements, or set of all elements such that this is the different ways of writing the same definition. Okay. So in this case, the kernel, in general, kernel of all so kernel of phi is equal to center of G. Okay. And therefore, we are getting ahead person, but G mod set of G. So this is anticipating, not anticipating. This is using isomorphism theorem, which we did not discuss. The first isomorphism theorem calculated. This is isomorphic to image of that phi, image of phi, which is in fact what is called the set of inner automorphisms of G. Okay. Inner automorphisms are exactly what automorphisms define this way. Okay. But G mod Z of G is isomorphic to inner order because it is not that every G defines unique automorphism necessarily. Different G may define the same automorphism. Automorphisms when we consider, you consider them distinct. So to take the set of automorphisms of this form, where every X is mapped to particular conjugate, right, etc., then this is isomorphic to that. Okay. Yeah. So, okay, we'll not going to like go faster. Is it okay? Or shall I go a little faster? These are very basic, right? You already know. We will do more advanced things. Yes.
Will they do meeting for 15 minutes?
Yeah, so we continue after 15 minutes.
If they are outside, you can go have a drink.
So this has to be consistent. Like you can't say that some elements are left side, some elements are left hand, some elements are left. That's not. And then identification. That's it. Yeah. Then so It is like so in every element, unlike the usual definition of identity, we're showing here that every element has some element which acts like identity on the right. But that is not a common. You have to prove that it's common. So this argument actually that's what. In fact, that will use it. So if we start with this, then same argument we have the right with that. So not we put the argument. Um, okay, suppose we were wanting x is equal to x. But you have given information in as cycle. Okay, so this is because if we dx now, dx is also equal to 0. So for any arbitrary value in g equal, y is also there in this setting. So that means so y belongs to dx means y is equal to some y prime equals x. So some y. Then we use this one. Then x is equal to so y is equal to x is equal to no, sorry, not like that. Take arbitrary y. Now we just do that dy is equal to g also. It's not looking special with x. Dy is equal to g. So there exists some x prime in g. As if x prime y is equal to x. Okay. Then we use so x prime y is equal to um, Okay. Earlier one is correct. And primes. Okay. Also one prime. Okay. But x is equal to x zero. So replace this primes. Then again replace y by x by y. So then we got that for this fixed e. Now we didn't take the e from somewhere else. The same e, but y's are if y is equal to y. So once you get this, you can use this to prove that E is a left identity, sorry, right identity for all. So similarly, inverting the staging order, you can show that there is some E prime such that E prime x is equal to x for all x. So this is for arbitrary. So similarly for all arbitrary groups. But once you get the left identity is there and right identity is there, so considering this as right identity, this is equal to E prime. Considering this as vector identity, this is equal to. So then, okay. So I'll tell you the big picture identity. Which is the top. The main thing what you need to think of is this. You can't do cancellation directly because this is two elements here, one element here. You can only do cancellation when you have two elements on both. Like something into say x into something is equal to x into something. Here that x into something is equal to x. So you're bringing that in. Why I'm considering more. Okay. So like y prime into x, then you're writing that y prime into x into. So here this element and this element. Uh, yeah. So it is not exactly cancellation, but yeah, the cancellation used here of making the target. But that's the point. You are replacing these two elements by three, and then going back to two. Okay. Well, yeah, well, it's just, because it is only correct. And I assume probably one other. That's what it is. Yeah, you send the total sheet or only display? Already. So what you're trying to do is no. Yeah, then we can do that. But on they get this. Yeah, you have it. Similar to normal subject, you will define ideas. Okay. Then what is going to be products of the gas product of product of sex, product of all these are good. What's the most important segment?
Yeah, we'll start the session soon. We are waiting for offline participants. Maybe after 5 minutes we'll start. Okay, well, start the session. If you have any question, you can ask right now. Sahib, do you have any question? You can unmute yourself and ask. Okay, I hope that all of you got the Q3 correct? Okay. So, past question we already discussed in the lecture. So, start solving question number 2. See whether you can solve it by yourself or not. See, what we have to prove? We have to prove that the function is continuous at the point half, but it is nowhere continuous other than half. Two things you have to do. Done. You can go on. Question number 4 I have already have solved the past half. Question number 2, 3, start solving. Yeah. Do sequential criteria. So consider a point, let's say a rational point, and consider a sequence of irrational converges to that point, and use the fact that if the function is continuous there, what will happen to the sequential criteria? Okay, so let's continue to solve that if it's continuous at half. So we have a function fx which is x if x belongs to rational intersection 0 1 and 1 minus x if X does not belong to this set. That means all irrational points from the set 0. So the thing is that suppose we have to prove that it is continuous at a point. So try to prove so that it is continuous at x equals to half. So now, if we just calculate this one, if x minus f of half, you see that let's say x is a rational number, then you have x minus half. If x is a rational intersection 0, and if irrational, then fx minus f of half will be 1 minus x minus half. Sorry. So it is nothing but half minus x. If x belongs to does not belong to Q in the section 0, 1. But obviously I mean to say that x belongs to 0. Okay. So in both cases, obviously, whatever epsilon you have, choose delta equals to epsilon, you are done. Okay. So for any given epsilon greater than 0, choose let's say delta equals to epsilon by 2. Then we are done. Because in that case, x minus half will be less than, if you consider x minus half is less than delta, that means it's a less than epsilon by 2. And therefore fx minus f of half is less than epsilon. So that's how we got the thing that f is continuous at the point half. Okay. Is it clear? After this point, just you need to choose whatever epsilon you can choose delta equals to epsilon by 2. You can actually choose epsilon, let's say epsilon by 2. Okay. To show that it is not at any other point, consider again that if we have a rational number, consider the irrational number and see what's going on. Like using sequential criteria. And similar to okay, so I'll show you for let's say the rational number. So let a sequence Rn of irrational in 0, 1, obviously, that converge to C. Okay. Now what about f of Rn? Because it's a rational, so f of Rn will converge to f of C. But f of Rn, so what we have, f of Rn, if it is continuous, then it should converge to f of C. But f of Rn is 1 minus Rn, which because Rn converges to C, so 1 minus Rn will converge to 1 minus C. And 1 minus C is not equal to C if C is not equal to half. If C equals to half, 1 minus C will be equal to. So that means if we have a rational number less than half, it is not going to continuous at that point. Similarly, you can show that if it is an irrational number, it is not going to come. So this problem is very easy. Okay. Hard one actually I ask you to solve it for yourself. So I'm not going to solve it. It's actually that definition. If C is a limit point, when the function is continuous at the point C, it can only limit degree. So do it later. Question number 5. Try to solve question number 5. Okay, what we mean by a function is additive. It is f of x plus y is equals to f of x plus f of y. Okay. We have a continuous function on R and the function is additive. If f of 1 is 1, prove that f is an identity function. Okay, so I'll note here. So what are the things given to us? Question number 5. Given that f of x plus y is equals to fx plus fy for all xy belongs to R. This is one fact. The other thing is given that f of 1 is 1. Correct? And say f is continuous on R. What you have to prove? To prove f of x equals to x or all x belongs to. Any idea how shall we approach? Can show that f of n is equals to n for every natural number. Okay, so first thing, try to show that for any natural number n, f of n is equals to n. Okay. That's easy, I guess. We can show it. Okay. So let n belongs to natural number. Then what? F of n can be written as someone else. F of n can be written as 1 plus 1 plus 1 n times. Okay. 1 plus 1 plus 1 n times. And then using the additive property of f, it's nothing but n into f of 1. Correct? F of 1 plus f of 1 plus f of 1. So it will be n into f of 1 if f is an integer. What about, I mean, positive integer? So what about if okay, so what about the f of 0? Okay, by the way, f of 1 is 1, so this is n. So f of x is x if n is a natural number. Okay. So f of 0, as you said, it is 0. Okay. Someone, is it? Can you see? I mean, for her it's fine. Anyone else can see it? F of 0 is 0. How to prove that f of 0 is 0? 1 minus 1. Okay, then. So it will be f of 0 equals to f of 1 plus f of minus 1. From there, how will get the value? Yes. We will take f of 0 as f of 0 plus 0, which is f of 0 plus f of 0, and by cancellation law, f of 0 is 0. Okay. So f of 0 is 0. So fine, for 0 it is working, for natural number it is working. What about negative numbers? F of 0 is 0. Now use that fact and what we can write. F of minus x, let's say x is a positive integer or something. But x is any real number, then what we can write. So let x belongs to what? Any number. Then f of 0 can be written as f of x plus minus x. Correct? Now by additivity, it is f of x plus f of minus x. And f of 0 we know that 0. So this implies that f of minus x is minus f of x. Correct. So therefore, if n is a negative integer, okay. Now should I write, let's say z minus, then f of n will be equals to, like, it is negative, so some minus into positive will be there. Okay. And this is same as f of minus k, f of k, and this is k, so it will be ultimately n. Correct? Where n equals to minus k, and k is a positive integer. F of n can be written as f of minus k, and f of minus k by this property minus of f of k, and because k is a positive integer, f of k is k, and then minus k is equals to n. Done. So if we have a negative integer, it's fine. Okay. Now go for rational number. Okay. Let's say x is a rational number. Then what do we have? Let x is of the form p by q. Then what we can write? We know that f of t is equals to what we can write? P equals to left side, then P equals to qx. Q is what? I integer, correct? It's a positive integer. We can make it in such a way that Q is greater than 0. If we have a negative number, take minus in the numerator. You'll have then P equals to qx. So can be written as x plus x. How many times? Q times. Correct? Because it's a positive integer, you can think about it. Now tell me what we can do. Next. Now it's very easy. Tell someone else. F of p equals to f of qx, and because qx is q time x, so by additivity q into f of x. Correct? Is it clear to everyone? Because q times x, so f of x plus it's a q time. Now f of p is an integer, so this is same as p. This implies that fx equals to p by q. Okay, so therefore f of p by q is p by q if f is a rational number. Okay, till now it's just an algebra and property of additivity, so algebraic property. Okay, we have not used anything, any concept of continuity of the function. Okay, now we have to use. So I will prove that f of x equals to x if x is an irrational number. Okay, so tell me, how can we do it? Let's say C is an irrational number. Then what we have to show? We have to show f of C equals to C. Okay, so we will consider a sequence of rational converges to C. Okay, so let Rn be a sequence of rationals such that Rn converges to C. Since f is continuous at C, since f is continuous at C, what we can write? F of Rn converges to f of C. Now f of Rn is equals to Rn because Rn are rationals. Okay, that is Rn converges to f of C. But we know that Rn converges to C, and you have unique limit. So by uniqueness, C equals to f of C. So we proved that f is an identity function. Okay, is it clear? Any question? So this is the only part we use the notion of continuity. Before that, we just use additivity property. Any question from online participant? Okay, no question. Okay, try to solve question number 6. So, similar type of question, but we change the condition that f is additive by this new condition that f of x plus y is fx into f of y. Okay, see what we are getting. We are getting either it's a zero function or f of x equals to f of 1 whole to the power x. So whatever f of 1. So for example, if f of 1 is 1, like the last example, then you will only get f of x equals to 1. It's a constant function. Otherwise, you will get f of 1 whole to the power x. So some a to the power x form. Okay, I give you 5 minutes. Try to solve it. Then I will see. whatever I'll write the conditions in the board. Question number 6. Even first thing first, so f of x plus y is fx into f of y for all xy belongs to R. This is given. Okay. Second thing, what is given? F is continuous on R. Okay. What you have to show? To show either f of x is 0 for all x, or f of x is a to the power x, where a is f of 1 for all x. I think first thing you can show is very easily that f of x is equals to 0. Did you get that part? F of x equals to 0 for all. Okay, good. Okay, some of you have solved it. So let's see one by one way. So first, what we have to see is what is the value of f of 0. Okay. So f of 0 plus 0 is f of 0 into f of 0, correct? And f of 0 plus 0 is nothing but f of 0. So f of 0 is equals to f of 0 square. So this implies that x equals to x type of thing. So this implies either f of 0 is 0 or f of 0 equals to 1. Correct. these are the two possibilities. F of 0 is 0 or f of 0 is 1. So let's say f of 0 is 0. Okay. So case 1, let f of 0 is equals to 0. Then what? Then for any x belongs to R, f of x plus 0 is f of x into f of 0. Then this means f of x equals to f of 0 is 0, so 0. Okay. This part is very clear. Case 2, if you write like this, it's nothing going, it will not give you any further information. Like f of 0 is 1, so you have fx equals to fx. So it is not that helpful. Okay. So case 2. Let f of 0 is equals to 1. So is there any way we can get the value of f of 1? Because we need the f of 1, correct? Somehow. So 0 plus 1 will be f of 1, will not be. Okay. Okay. So in the question is we have only f of 1. We're not going to get any specific value of f of 1. But okay. Let's see. How will approach? No, f of 0 is not 0. F of 0 is 1. Okay, first of all, let's see what's going on. Let's say C is any real number. Then f of c by 2 plus c by 2, which is f of c, can be written as f of c by 2 into f of c by 2. So obviously this is a positive number, correct? So I mean non-negative number. Whatever f of c by 2, this will give you f of c by 2 into f of c by 2 is non-negative number. Okay, that's the thing we can derive. Similarly, f of 0 is like f of c minus c, right? Which can be written as f of c into f of minus c. And f of 0, we know that this is 1. So from these two, what we can say that f of c is always greater than 0. It cannot be equals to 0, because if f of c is 0, then 1 is equals to 0. That is not possible. So from these two imply that f of c is a positive number. That's the one thing we can say. Okay. So another thing we can also see that whatever f of c is a 1 by f of c. If we know the positive value of the positive integer, then we can also know the value of the negative integer by just f of minus c is f of 1 by c. But let's see what is the value of the positive integers. So let's say n belongs to the set of a natural number, like we did in the last case. So what we can write, then f of n can be written as again like 1 plus 1. 1, how many 1? are there n numbers. Now this is same as f of 1, f of 1. How many f of 1? Yeah, n times. N times. So it's like f of 1 whole to the power n. Correct? So whatever f of 1, it will be f of 1 whole to the power n. So therefore, that f of x equals to f of 1 to the power x is true if x is a positive integer. Correct? So we are getting up to this point that f of x equals to a to the power x if x is a positive integer. And obviously, okay, now what about negative integers? Let's go for the. So for negative integers, by this property, we can write. So if n belongs to this minus j, then okay, like then n equals to minus k for some positive integer k. Okay, and f of n will be f of minus k, and which is 1 by f of k, and f of k is f of 1 whole to the power k, and which is f of 1 whole to the power minus k, and minus k is so even for the negative integer it is working. Fine. Now what about rationals? Try to solve it for rationals. So again, let's say let x belongs to R and x is of the form p by q, where p, q are integers and q is greater than 0. Look at last workout example. So from there, what we can write. I think you can now solve it very easily. It's not that tough. So again, we'll write p equals to qx. So we'll write f of p equals to f of qx. Now q is a positive integer, means you can think it's you are adding q numbers of x. So therefore it is f of x whole to the power q. Okay? Because now we have f of x plus y equals to f of x into f of y. You have f of x into f of x, q times f of x. And f of q is a integer, so it is f of 1 whole to the power p. So therefore, f of x is, I should not write this way. Okay, f of x is f of 1 whole to the power p by q. That's what we have to prove, which is f of 1 whole to the q. Next part, what we'll do? So yeah, continuity. You use sequential criteria that you have a sequence of rational converges to that point, and then whatever we did in for the last example, do it the same. Okay. So I'm leaving it to you. So we'll care. Okay. Okay. By the way, any question? Okay, question number 7 is again that equivalent definition thing. So try to solve that. I'm not going to solve it. So solve it later. Prove that if f is a continuous at C, then limit h tends to 0, f of c plus h is f of c. Okay, just simple using epsilon delta definition. Okay, question number 8. Again, I'll give you 5 minutes to think. Show that an additive function is either everywhere continuous or nowhere continuous. That means what? Either it is continuous everywhere or nowhere continuous. So that means try to solve that, assume that function is continuous at a point, and from there try to show that it is continuous everywhere. If it is nowhere continuous, then nothing to show. You have nothing to do. So let's say it's continuous at a point, and from there try to show that it is continuous everywhere. Okay, I write the information. So question number it is 9, right? 8. What is given? F is 1, f is f of x plus y, it's fx plus f of y. So it is additive. Second thing is that f is continuous. Oh, it's not given that it's continuous. If it is given, then nothing to show. Any other thing is given to us? No, correct? It's just it's a additive. So what you have to show is that to show one either f is nowhere continuous or f is everywhere continuous. So there are only two possibilities. If it is nowhere continuously, we have nothing to show. Just assume that it is continuous at a point. At least one point is there where it is continuous, and from there derive that f is continuous everywhere. Okay, I'll give you a hint. Try to use question number 7 to solve this problem.
So what you have to show, if you are planning to use question number 7, you have to show that limit h tends to 0, f of x plus h is equals to f of x. Okay, let's assume that f is continuous at 0. Then actually it's not mandatory that you have to assume that f is continuous at 0. Yeah, it's, let's say it's continuous at a point. So you can only say that there is a point C where it is continuous. From there you have to get that it is continuous everywhere. Obviously, you have to use the fact that it is additive. Okay, so go one by one. Let C belongs to R be a point such that f is continuous at C. Then what we can write, use question number 7, limit h tends to 0, f of C plus h equals to f of C. Now then what we can write, f is additive, so what we can write, limit h tends to 0, f of C plus f of h equals to f of C. Now h tends to 0, f of C is f of C. So f of C is cancelling out. So what we are getting, limit h tends to 0, f of h equals to 0. Now from there what you can write, zero is okay, but yeah, for any x just use the same thing. So now yeah, additivity, x belongs to R, then limit h tends to 0, f of x plus h is now limit h tends to 0, f of x plus f of h and fx plus limit h tends to 0, f of h, and this is fx because this part is 0. Okay, now it's very simple. Is it clear to everyone? It's very simple problem, but a little bit tricky. Okay, by the way, it's not included over here. So try to get some data from the fact that, let's say, f of x plus y is now fx into f of y. Then what we can derive from that? Okay, in this question we have f of x plus y is fx plus f of y. Now assume that f of x plus y is fx into f of y. Can we derive the similar result? Like either it is continuous or not continuous. Can you derive that type of result? So what I am saying, okay, let me be clear. So let's suppose I give you this, that f of x plus y is fx into f of y. Now, so let's say it is continuous at a point. So second thing is that f is continuous. Okay, let's first example, I'll give you that f is continuous at 0. Next, I will ask if it is not 0, what will happen? But first, let's say it is continuous at 0. Then what we can write? Can we say that f will be continuous everywhere? Okay. The question is, can we say that f is continuous everywhere? Why real numbers is important? I mean, we are all working real number. No, whenever we are discussing on the whole real line. Like nothing is mentioned means on the whole real line. Continuous means everywhere means on the whole line. No. Okay, again you can see that f of 0 plus 0 is f of 0 into f of 0. So f of 0 will give you that f of 0 is 0 implies that f of x will be 0. So it will be 0 function. So one thing is very clear. So you will have a 0 function. One case is that you will have a 0 function. Is it clear? Like what we did in that example number 6. One case is f is a 0 function. Next case is that f is non-zero function, like f of 0 is equals to 1. Okay. So one thing we can derive from this, so either f is a 0 function or what we have, f of 0 is equals to 1. Okay. Now we use that limit h tends to 0. F of x plus h. So first of all, you have to say that it is continuous at the point 0. So f of 0 plus h will be f of 0, which is 1. Correct? It's given that f is continuous at the point 0. So therefore, limit h tends to 0, f of 0 plus h will be f of 0, and f of 0 is 1. Now f of 0 plus f of h is f of 0 into f of h. So this will imply that, what it will imply? Limit h tends to 0, f of h equals to, it is 1, correct? F of 0 is 1. F of 0 plus h is f of 0 into f of h. F of 0 is 1. So we have limit h tends to 0, f of h equals to 1 only. Then you have, suppose we have another point, f of x plus h. Then what will happen? H tends to 0. Okay. F of x plus h will be limit h tends to 0, f of x into f of h. and this is what? So it is continuous at the point x. So what we learned that if it's continuous at the point 0, then obviously it will be continuous everywhere. Okay, either it's a zero function. Zero function means it's obviously continuous everywhere. If it is a non-zero function, then still it is continuous everywhere. Okay. Now, can you find an example where f is continuous at one point, but it is not continuous? I cannot say, like in this case, what we assume? We assume that it is continuous at 0. Suppose you know that it is continuous at a particular point, a non-zero point. Can we have this similar type of relation? So why 0 is important? You see that we use this fact, f of 0 plus h is f of 0. If it is something else, you cannot use that fact. Okay. So that's why in this condition, it's continuous at 0 is very important. Okay. If it is not, then see what will happen. I'm not going to discuss that, but think about examples, or like suppose it's given in a some point C which is non-zero point. Can we conclude from there whether it is continuous or not continuous everywhere? Okay. Everywhere means whole real line. Okay. Any question? No. Okay. You should ask question. Why are you not asking question? Okay. Question number 9. Let f from R to R be a non-zero continuous function on R. Okay, non-zero continuous function means at least there is a point where f of x is not equals to 0. Show that there exists a rational number q such that f of x is not equals to 0. So that means you cannot say that if we have this condition, so f of x can be 0 for all rational numbers. Look at the question again. Think about it. It's a non-zero continuous function on whole real line. So you have to prove that there is at least one rational number where the function takes non-zero value. Okay, hence is use sequential criteria. So try to prove by contradiction. Assume that f of x is 0 for all rational number, and try to get a someone raised. Neha, what is your question, Neha? Hello? Hello? Neha?
Yes, sir.
Yeah. Let's tell your question.
Sir, I have a solution. I want to propose a solution. Yes, sir.
Yeah. Okay. Go ahead.
Sir, since it is a non-zero function, there must exist a real number for which f of alpha is non-zero.
Okay.
We can then consider a sequence of rational numbers which converges to alpha.
Okay.
Then since the function is continuous, the sequence f of xn should converge to f of alpha.
Correct.
Yes, sir. Since we have assumed that f of x is 0 for all rational numbers x, the sequence is nothing, f of xn is nothing but a null sequence, whereas
Yes.
f of alpha is non-zero number.
Correct.
This gives us contradiction.
Yeah, that will give us a contradiction. Fine. Correct. So did you get the solution? What she said? So she said that consider a point C where the function is not equals to 0. From there, you get a contradiction. Okay. Use the sequential criteria. Not? Okay. If you are not getting it, let me write it down. So question number 10 or 9? 9. Okay. So suppose on contrary that f of x equals to 0 for all x belongs to rational. Yeah.
We assume that there exists a point C where f of C is.
No, what you have to prove that? Go ahead.
We assume that f of C.
So f is a non-zero continuous function on R. You have to prove that there exists a rational number at which f of x is not equals to 0. So what is the contradiction of it? I mean, what is the opposite statement? For every rational number, it is 0. Okay. From there, we have to. Oh, okay. Go ahead.
So we will have a rational point, but at least one point where the value
Not equals to 0 because function is a non-zero function. Correct.
let's say f of C is not equal to 0.
Correct.
Then C will be an irrational number.
Correct.
So we can have a sequence of rational numbers.
Correct.
So since it's continuous, let's say xn converges to C. So if of xn converges to f of C, since xn is a rational number, f of xn is 0. So we have a sequence of 0 converging to 1.
Correct. Yes. Same thing. That Neha said the same thing. Okay. So you can say that, let's say there is, or I can prove in a different way. Let's say C is a real number. Okay. Any real number, rational or irrational, does not matter. So there are always going to exist a sequence of rational converges to C. So let Rn C for the C be a sequence of rationals converges to C. Okay. Since f is continuous at C, since f is continuous at C, what will happen? F of Rn C converges to f of C. Now, because Rn's are rationals, so we have a sequence of zeros converges to f of C. But 0 only converges to 0. I mean to say that sequence of zeros converges to 0. This implies that f of C equals to 0. Correct? Now C is arbitrary. So f of x equals to 0 for all x, which contradicts the fact that f is a non-zero function. Okay. So thus f of x equals to 0 for all x belongs to R, which is a contradiction. Hence, complete the sentence. There exists a point rational number at which. So can you weaken some condition and do some? I mean, this is your task to make another question similar to type of this type. I mean, similar to this type of question. Like you see that in the question, what we learned that if we have a function which is 0 for all rational numbers, and you know that a function is continuous at a particular point. So here we did not use the fact that f is continuous at the rational points. What is the fact we use? We use the fact that f is continuous at a point C. So now instead of saying that f is a non-zero function and all sort of thing, what we can say that let's say we have a function f such that f of x equals to 0 for all rationals, and f is continuous at a particular point C, then obviously f of c should be equals to 0. Okay, this is the one thing you can also make such type of question. Is it clear what I said? Okay. So from one question you can make several type of question, just looking at the conditions and prove inside a theorem. Okay. Question number 10. Try to solve question number 10. It should be 0, but it's somehow become 1. So f is -1 to r be continuous at the point 0, and f of 0 is equals to 0. If f of x equals to f of x square for all x belongs to -1 to 1, prove that f of x is 0 for all x belongs to -1 to 1. Again, you have to use sequential criteria. Okay, so let me write down what are the things given to us. Why this? Yeah. So question number 9, given is that 1, f is continuous at 0 and f of 0 is equals to 0, correct? Second thing, what? F of x equals to f of x square for all x belongs to R. What we have to prove? F of x is equals to 0 for all x belongs to R. That means f is also going to be a continuous function. Oh, sorry. Let's see. Wait a second. Yes, it's a -1 to. So, because it's given, it's continuous at the point 0. So somehow we have to find a sequence which converges to 0, and then use the fact. Think about it. First of all, can you see this one? For any C, let C belongs to the set of all real, any real number. So f of C is f of C2 to the power n for all n belongs to set of all natural numbers. Is it clear? 2n or 2 to the power. So power of power. C square whole square, then C square. So how we are getting it? F of C is f of C square. Then f of C square is f of C square whole square. So that means 2 square. Correct? Then whole square again. Okay. Or you can write yes, that will use the fact. Okay, C square whole square, then C square whole square whole square. Okay. That is C cube. So C square whole square, this one. Something is not right. Yeah, it's fine, correct. Okay. Yeah, sorry. Again, that's the same thing. Okay, anyway, you can write the real number. Okay, if you go on in this way, so f of C 2 to the power n. Okay, now use the fact that C of 2 to the power n converges to 0 because 2 to the power n converges to like infinity type of thing. If n tends to infinity, 2 to the power n also converges to infinity. And because C is in between -1 and 1, now you have to use that fact. Because it is in between -1 and 1, that means absolute value of C is less than 1. So therefore, C of 2 to the power n converges to 0. Okay. So since absolute value of C is less than 1, C of 2 to the power n converges to 0 as n tends to infinity. Now using the idea that fact that f is continuous at 0, what we can write? So since f is continuous at 0, so f of C 2 to the power n converges to f of 0, which is 0. Now f of C to the power n is nothing but the constant sequence. So f of C converges to 0. Therefore, f of C equals to 0. Since C is arbitrary, so it is 0 for every. So we prove that. Great. So actually, whatever f of 0 it will be, you will have the idea. Like if f of 0 is a k, then all the value of the function will be equals to k. Okay. Is there anyone to catch bus or something like that? Otherwise, I'll just solve problem number 11 and then leave. Okay. 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 First of all, what is question number 11? It's another characterization of continuous function. Okay. To prove that a function is continuous on R, if and only if the inverse image of an open set of R is open in R. It's like a theorem. You have to prove it. So if F is continuous on R, if and only if F inverse U is open in R for every open set U of R. One part is very easy. Which part? Actually, both parts are easy, but one part is like trivial. So note that we assume the definition of continuity that it's a neighborhood. Neighborhood is an open set containing that point. So let's assume that, okay. So let F inverse E is open in R whenever U is open in R. So you have a function from R to R and you have an open set U. So pre-image of that open set, this is F inverse U. So you have to prove for each open set U of R, F inverse of U is open over here. Okay. This is given. What you have to prove that it is continuous at each point of X. Okay. So let's take C belongs to R. We have to prove that F is continuous at C. Okay, we have to prove that it is continuous at C. How to prove it? It's very simple. So what we'll do? Which way? Which property we are going to use? Epsilon delta. Okay, let's say we're going to use epsilon delta property. So that means, let's say epsilon greater than 0 be given. So we have a pre-assigned positive number. Okay. So let epsilon greater than 0 be given. Then consider open set f of c minus epsilon comma f of c plus epsilon. That open set you have to consider, because given that you have an open set in the codomain, from there you will get an open set in the domain. So that means you have to, whatever you have to consider, you have to consider in the codomain set. So like C is a point, now it's mapped to a point f of c over here. That means you have to consider point in the codomain. Okay. So let the open set U equals to f of c minus epsilon, comma f of c plus epsilon. Okay. We have a real line. Here you have f of c, and you have f of c plus epsilon. Here you have f of c minus epsilon. This is the open set we are considering. So by given consideration, what will happen? The pre-image of this open set is open. Okay. So by assumption, F inverse U is open, correct? And you can see that C is already there in F inverse U. Okay. Open. That is, so what will happen? That means what? Open means, and okay, we need to erase it. And C belongs to F inverse U. Now, because C is an element of an open set, that means C must be an interior point. So therefore, there exists a delta greater than 0. So therefore, there exists a delta greater than 0 such that C minus delta comma C plus delta subset of F inverse U. Okay. And you can clearly see that F of C minus delta comma C plus delta is now subset of F of C minus epsilon comma F of C plus epsilon. So thus F is continuous at the point C. Here is it subset, because whatever x you will choose over here, x will be in F inverse U, therefore Fx will be in U. So therefore U means this one, F of C minus epsilon, F of C plus epsilon. So this implies this one. So that is the definition of continuity. Okay. Epsilon delta definition. So this implies that F is continuous at a point C. Now C is an arbitrary point, therefore it is continuous everywhere. So this part is very clear. If we assume that if we have an open set and the image of an open set is open, then it is continuous. Okay, what about the other part, converse part? So let's say if it is continuous, you have to prove that the image of an open set is open. So that means what you have to show that each point is an interior point. Okay. So conversely, okay, I'll do it fast. Let F be continuous on R. Let U be an open set in R. We have to show F inverse U is open in R. Okay. So that means let C belongs to F inverse U. What you have to show? It is sufficient to show that C is an interior point of F inverse of U. So it is sufficient to show that F, sorry, not F, C is an interior point of F inverse C. Sorry, F inverse U. Okay. Now, since F is continuous and C belongs to F inverse U, so F of C belongs to F of U. Okay. Since F is continuous at C and F of C belongs to U. Why F of C belongs to U? Because C is in F inverse U. Okay. So then there exists an open set V containing C such that F of C, sorry, F of V subset of U. That's the definition of continuity. Or you can use the fact that there will exist a delta greater than 0 such that F of C minus delta comma F of C plus delta is a subset of U, whatever fact you will use. So now this will imply clearly C belongs to V subset of F inverse U. So hence C is an interior point. Thus C is an point of F inverse. This proves that F inverse AU is an open set. So that is the actually it's a theorem, or you can use as an exercise, because every theorem is an exercise. In every exercise you can treat it as a theorem. If it's, I mean, not every exercise you can treat as a theorem, but somehow you can mold it and make a theorem. Okay. So next is question number 12 that we'll do in the next step. Okay, that's all for today. If you have any question, online participant, do we have any question? Okay, then we'll meet again tomorrow at 9:30, sir. Okay, please join the meeting at 9:30 using the same link. Okay, then I am